Welcome back to another video. A point estimate is a single numerical value used to approximate an unknown population parameter, for example, theta. This value is calculated from a statistic, for example, theta hat, which is derived from sample data. The statistic used to calculate the point estimate is called the point estimator. For example, the sample mean x bar serves as the point estimator for the population mean mu. The sample variance, s squared, is the point estimator for the population variance, sigma squared. The sample proportion, p bar, serves as the point estimator for the population proportion, p. The difference in sample means, x1 bar minus x2 bar, serves as the point estimator for the difference in population means, mu1 minus mu2, and finally the difference in sample proportions, p1 bar minus p2 bar, serves as the point estimator for the difference in population proportions, p1 minus p2. While point estimates provide a concise and practical way to estimate population parameters, they are subject to sampling variability and do not account for the uncertainty inherent in the estimation process. The central limit theorem is a fundamental concept in statistics that states that, regardless of the population's original distribution, the distribution of the sample mean, sometimes even other sample statistics, will tend to be approximately normal as the sample size increases, provided the samples are random and independent. This holds true even if the population itself is not normally distributed. The central limit theorem becomes more accurate as the sample size grows, typically when the sample size is greater than 30. The theorem also tells us that the mean of the sampling distribution will be equal to the population mean, and the standard deviation of the sampling distribution will be the population standard deviation divided by the square root of the sample size. The central limit theorem is crucial because it allows for the use of normal probability methods in inferential statistics, even when the underlying population distribution is unknown or skewed. Here, we are hypothesizing on the population mean when the population variance is known. As a result, we are using a z-test or a normal test for all these three cases. To find the value of the z-test, we need to plug in the values of sample mean, x bar, sample size, n, the hypothesized value, mu0, and known population standard deviation, sigma. In case A, a two-tailed test, we are testing for deviations in both directions from the hypothesized value. This means that we are interested in whether population mean is either greater than or less than the hypothesized value. For example, suppose we want to test whether the mean weight of a product is different from the standard weight. The null hypothesis would state that the mean weight is equal to the standard value, while the alternative hypothesis would suggest that the mean weight is different. To calculate the p-value for this test, we first find the value of the z-test statistic, and then we calculate the probability of observing a z-test statistic as extreme as the one we found, in either direction. This is the highlighted area in part A bottom figure. This gives us the p-value, which helps us decide whether to reject the null hypothesis. If the p-value is very small, it suggests that the observed result is highly unlikely to happen by chance, so we reject the null hypothesis. The rejection region for a two-tailed test consists of both the upper tail and the lower tail of the normal distribution. If the test statistic falls within either of these regions, we reject the null hypothesis. These areas are determined by the chosen significance level. If we set alpha at 5%, the rejection region is split equally, with 2.5% in each tail, from negative infinity to negative z-value of 1 minus half alpha and z-value of 1 minus half alpha to positive infinity. We will reject the null hypothesis if z-test statistics falls in this rejection region. The upper-tailed test, case B, is used when we are specifically testing whether the population mean is greater than the hypothesized value. For example, imagine we are testing whether a new material has a higher average strength than the current standard. The null hypothesis would state that the mean strength is less than or equal to the standard strength, and the alternative hypothesis would suggest that the mean strength is greater than the standard strength. In this test, the p-value is calculated by finding the probability of observing a z-test statistic greater than the one we calculated. If this p-value is small, it indicates that the observed value is unlikely to occur under the null hypothesis, leading us to reject the null hypothesis in favor of the alternative. In this test, the rejection region is in the upper tail, meaning we only consider whether the z-test statistic is significantly large. If the test statistic falls within this upper rejection region, we reject the null hypothesis in favor of the alternative. The size of this rejection region is determined by the significance level, such as 5%. The lower-tailed test, case C, is used when we are specifically testing whether the population mean is smaller than the hypothesized value. For example, suppose we are testing whether the average lifespan of a particular battery is less than the stated value. The null hypothesis would state that the average lifespan is greater than or equal to the stated value, and the alternative hypothesis would suggest that the average lifespan is less. In this case, the p-value is calculated by finding the probability of observing a z-test statistic smaller than the one we calculated. A small p-value suggests that the observed result is highly unlikely to occur under the null hypothesis, leading to a rejection of the null hypothesis. In this test, the rejection region is in the lower tail, meaning we only consider whether the z-test statistic is significantly small. If the test statistic falls within this lower rejection region, we reject the null hypothesis in favor of the alternative. Again, the size of the rejection region is determined by the chosen significance level. Let's go over an example together. Suppose the mean weight of a flock of sheep was measured by their shepherd as 16.4 kilograms last year. In a sample of 35 sheep this year, the mean weight is 15.6 kilograms. Assume the population standard deviation is 2.5 kilograms. At 0.05 significance level, can we reject the null hypothesis that the mean weight has reduced compared to last year? Please pause the video and try to answer this question on your own. First, we need to define the null and alternative hypothesis. As the main claim of interest is observing an increase in weight, we define the alternative hypothesis as mu being greater than 16.4 and null as mu being less than or equal to 16.4. To choose the test statistics, we need to identify that we are hypothesizing on the population mean of a single sample and the population variance is known, so we must use a z-test statistics for single samples. We can find the value of our z-test statistic by plugging in the values of x bar, the sample mean, mu0, the hypothesized value of population mean, sigma, population standard deviation, and n, the sample size, as 15.6, 16.4, 2.5, and 35, respectively, which is minus 1.893. Next, we need to use a rejection method. If we use the rejection region approach, we need to find z-value of 1 minus alpha or z of 0.95, which is 1.64. Our rejection region is 1.64 to positive infinity. As our z-test does not fall into rejection region, we fail to reject the null hypothesis. For the p-value approach, we need to find the probability of observing even more extreme values, which equals to 1 minus the CDF of our z-test value. This probability is 0.97, which is greater than alpha. So, again, we fail to reject the null hypothesis. To use Python for hypothesis testing on the population mean when variance is known using a single sample, we need to load the z-test single function and pass the necessary arguments. Here, we have a sample of size 30 of height of Italian men. Knowing that height in Italian men has a variance of 25, we want to know if we claim that the average height of men in Italy is not 168 cm at equals 0.01. So we need to run a two-sided hypothesis. Once the function is loaded, we need to pass the sample data, the hypothesized mean, the population standard deviation, alpha, and the alternative hypothesis, which here is a two-sided test. The function will return to us the corresponding z-test, p-value, and a two-sided confidence interval by default. If you want to use the rejection region approach, you can use Python to directly retrieve it. As you may remember from the Type 1 and 2 errors video, Type 2 error happens as a result of failing to reject the null hypothesis when it is false. In hypothesis testing, it translates to mu being equal to another value compared to what hypothesized under the null hypothesis, mu0. As alternative hypothesis is true, let's assume the true population mean is equal to mu0 plus delta. It means that if we want to correctly standardize x bar, instead of deducting mu0, we should subtract mu0 plus delta. As a result, the z-test statistic that we previously defined is following a normal distribution centered at delta divided by sigma over square root of n instead of 0. Now, if we want to measure type 2 error, the probability of failing to reject the null hypothesis when it is false, we need to find the probability of the true standard normal statistic being between outside the rejection region, between negative and positive z-values of 1 minus half alpha. To define the optimal sample size for a two-tailed test, we want to find a sample size that guarantees certain values type 1 and 2 errors. Simplifying the type 2 error to the cumulative probability of z-value of 1 minus half alpha minus delta divided by sigma over square root of n, we can find the optimal sample size for a two-tailed test as square of summation of z-values of desired beta and 1 minus half alpha multiplied by sigma squared and divided by delta squared. Please remember delta measure how far the actual and hypothesized means are. For example, the sample size for a two-tailed test to guarantee alpha of 5% and beta of 10% when delta is 2 and the variance is 4 is 11. Please try to find the optimal sample sizes for one-tailed tests. Thank you for watching this video.
See you in the next one.